It's actually great to be here. This is the first time that I've actually been at a user conference, although a very long time programmer using R and S plus and S before that, and we'll even have a plug for Fortran too. So, all right. So, for those of you who haven't had consumed all the Kool-Aid, what is Bayesian model averaging? Okay, so as anyone knows who's taken an elementary statistics course, when you start doing regression, model uncertainty is really pervasive. There's always a question, what variables do we put in the model? Hopefully a lot of our methods have gotten better. We're no longer doing kind of stepwise search, but often there are a number of even more modern methods that still end up selecting a single, quote, best model. And so Bayesian model averaging is kind of an ensemble method. It takes a different approach. So rather than just selecting a single model, we're going to develop a kind of principled approach to account for that model uncertainty by averaging predictions over models. And here those weights are given by the amount of support each model gets from the data based on this posterior probability. So just as a motivating example, start off with, again, ordinary least squares or regression. And so again, we may have a case where we don't know what are the best predictors that should go into the model. So if we have a full model that might have, say, P possible predictors, those might be your original variables in some data frame. They may be other transformations. Again, the method is kind of agnostic to what those X's are. But of course, if you have P predictors, if you can consider all possible subsets, there are 2 to the P possible models, and that grows very rapidly. Now, of course, classical model selection really ignores this uncertainty. So how many of you have a 401k or some form of retirement plan? Okay, if you don't, you should start saving. How many of you have yours invested in just, say, one stock? One. You don't select the best stock, right? You use an ensemble of methods, okay? And so again, that's the point. You don't want to necessarily put all your eggs in one basket. You want to average over some of the risk associated with different models. Okay, so behind the Bayesian model averaging approach, again, the kind of simple steps would be to specify the model space. Which predictors are you entertaining to put into your model? Again, the devil's always in the detail. You have to assign priors to all of the models and the parameters. However, there's been a long history of research that has provided kind of support for what are some of the better methods for how to do that. Next step, of course, is computing the posterior model probabilities. That in itself also involves some challenges. But again, there are some very good approximations if you can't do it analytically. And of course, then once we have all those ingredients, then we're going to just average our inference across models where the weights are proportional to their posterior probabilities. Okay, so again, as many people have described kind of Bayesian methods, it's putting in all the things, turn the Bayesian crank, and out comes the answer. Again, how you get to that is always, is often challenging. Okay. So in terms of just that basic kind of mathematical formulation, we have to compute these posterior model probabilities, and so those have ingredients. We have to have a prior probability on each of the models. That could be subjective, but there are more objective methods that one can also try to use that have good properties. Okay, and then the other part in the numerator here is the, again, this is probability of the data given the model. That is, again, the likelihood of the data conditional on that model. Okay. Now that doesn't have any other unknown parameters in it. The only thing that is conditioning on is which model we're looking at. So that's where, again, some of the details go into actually computing that. Okay. And of course, then in the denominator here, we have a sum over all possible models. Well, as you know, when we try to take a census of the US population, do we enumerate the population? No, we sample. Okay, and so again, that's one of the beauties behind a lot of the growth of Bayesian methods, that we don't necessarily have to, again, enumerate the whole population. We can use sampling methods to get at that. Okay, and so then if we have those components, if we can compute, say, if we're interested in, say, making the mean prediction or kind of a forecast, we can compute that conditional on each model, and then we're going to weight those predictions or estimates by their respective model probabilities. Right, and so again, the ingredients that go into computing this kind of marginal likelihood of the model, it's going to balance kind of the goodness of fit of the model. A lot of the methods that I'll talk about, I won't give the formulas for that, but they're functions of the ordinary R squared. Okay, so as a measure of the fit of the model, but they balance the model complexity. Okay, and as we know that we can keep throwing more and more variables into the model, improve R squared, but when it comes to out-of-sample prediction, that is a bit risky. Okay, so why might you want to use Bayesian model averaging? Well, it avoids overconfidence in just using a single model. It's been shown in a number of cases, and there's also theory to support that. It can improve predictive inference over just using a single model. And it can also facilitate variable selection and inference, again, incorporating that model uncertainty. And so, you know, there are situations where you will need to select a model. Variables have different cost, and so in terms of production, you might need to use some of that utility in trying to decide what is a best model. Okay, and so there's ways that one can incorporate that. Of course, what are the challenges? Why isn't it as widespread as other methods? Again, like the lasso, well, a lot of it comes down to software. Again, trying to compute some of these things from scratch, that can be challenging as well as being inefficient. So that's been the goal of this package that I've been developing over the years, is trying to get methods out there that people could use if they do want to try to explore it in practice. All right, so the BAS package, so BAS stands for Bayesian Adaptive Sampling. Early variations of it were based on kind of efficient sampling without replacement algorithm. The idea is that we visit a model, we compute all these quantities, we don't need to go back and resample it, but it does have other ways of doing MCMC to get kind of more population unbiased estimates. So it's been coded to try to be fairly efficient. It handles linear regression and generalized linear models. And I've tried to write the package so that it has a similar syntax so that users who are used to using LM or GLIM can adapt to it fairly easily. Okay, and so it can enumerate models if that's possible, but in many cases where P is large, that's not feasible, and so it uses efficient sampling to try to explore those models based on their posterior probabilities. And a lot of the guts are coded in C and Fortran, so that can make it much more efficient. So particularly, we're fitting millions and millions of regressions, and so trying to do that where it scales with P as opposed to scaling with N. Okay. And again, it's available on CRAN, or if you have an issue, you can go to GitHub. Development version has more of the fixes there. All right, so just a simple example. If we use the CARS data set, we can just fit the model. So BAS.lm is the substitute for LM, and you can see it has the usual kind of syntax where we have model formulas and provide a data frame for that. And there are a lot of other options. So again, in the help file, you can change a lot of the specifications, but this uses just kind of a default specification in prior. Okay, and if we do a summary of that, we can see from this, it's a little bit different than the summary that you would get from LM. It has kind of the first column there corresponds to the posterior probability that a variable is included, something that might be analogous to a p-value and has all the same pivots or pitfalls of interpreting, as well as some of the p-values. But it just shows you what were the first 5 models, and the ones show which variables were included, the zeros show which variables are excluded. So it just gives you kind of a snapshot of that. Their posterior probabilities for each of those variables being included in some of the or posterior probabilities of that model. And so you can see in here, out of there are 1,024 possible models, the highest model has a posterior probability of 0.15. Okay, so there's a lot of uncertainty over those different models as to which one is exactly the best. Okay, so there's some other summaries there. If you want to just look at a kind of plot summary, as in LM, we have a usual kind of residuals versus the fitted values. These fitted values are computed under model averaging. And again, you can try to look at, are there outliers? Are there other things that you might be concerned about with the model? The bottom picture in the lower left shows kind of the model complexity plot. So it's looking at that log marginal, that was the evidence there in the data, versus the dimension. And so it gives you kind of an idea of which models are, have higher support, what's that trade-off between the dimension of the model and the evidence for the model. Okay, and in the bottom, we mentioned those posterior inclusion probabilities. That was the marginal probability that a variable is included. So that's just a plot of that to get a kind of a picture marginally of which variables might be important. And so with this, we can see that, again, weight is the most important variable, but there is uncertainty about some of those others. Okay. And again, just like with p-values, if you've got correlated variables, that's going to dilute these inclusion probabilities. So that's where just because something's low doesn't mean it's not important. Another way of trying to visualize the model space, and so this is for, again, looking at the top 20 models. So for each column of this image, we have a variable, and then, again, the log posterior odds relative to the lowest model in this group. Okay. And so you can see in this that within these top 20 models, the top model is about, again, on the log scale, 2.9 times higher than the worst model in this group. The black indicate where the variables are excluded, and then the colors reflect where variables are included in the different models. And again, with this picture, as in previous, we can see that weight is included in all of those top models, but again, in the second best model, the second row there, then we have the horsepowers coming in. So again, you can see the trade-off between some of the variables and what are in the top model. So a little bit better than that first summary, which just showed the zeros and ones. If you want to extract coefficients, there's a coef function. You can get confidence intervals or Bayesian credible intervals. And so that is actually based on what are called HPD intervals. So they're not necessarily symmetric. And so we'll see in a different way of visualizing that, why that comes about as being important. Okay. But these are the model average coefficients, and these credible intervals are based on that ensemble of models. Okay, and so if we look at that, you can see here that in terms of some of these HPD intervals, some of them are they touch zero, so they're not like a typical 95% credible interval that might be symmetric. So they actually, if there's a high probability of a coefficient being non-zero, it's not going to include zero, but in some cases, if the amount of mass that is in the model that says the variable's in zero, we might have the credible interval actually just be there at that boundary. Right, and so that's where you can see that some of them, in terms of these intervals, are very tiny. This also includes the intercept, which is included in all the models. So again, the scaling here, it's better if I go back and just delete that to get a close-up of what's going on. Okay. There are functions for doing predictions under model averaging. So again, the usual kind of syntax, there's fitted, predict. You can predict with new data or ensample. You can get credible intervals, confidence intervals for, again, those prediction intervals, or for the posterior means using confident. And then there are plotting functions that also summarize that. Okay. And so, as I said, it can be used also for variable selection. There are ways of getting what would be the kind of the best model under different types of utility functions. And so those are options there. Whether someone wants to write their own custom function, again, of course, that's what's the beauty of the whole R ecosystem, is that you can contribute to the packages. Okay. So that was just one simple example illustrating it. I guess I'd like to highlight a paper that's by Adrian Raftery and one of his students, Porwal. This appeared in PNAS in 2023. And they went back to try to ask the question of, like, well, there are all these different methods for model selection and learning. You know, how can we do a comparison of them? And so they basically did a very large bake-off. This is all under regression. So there are different numbers of data sets, a lot of them coming from the, again, machine learning repositories, but kind of varying the sample size in as well as the dimension of the problem here. And so these were examples that they looked at. And so they compared 21 different methods. And out of these, and I don't know if you can see them, but the top 4 rows skipping the horseshoe, the EB, empirical Bayes, benchmark, those were all methods that were implemented with the BAS package. Okay. And so what they did is they did a comparison of different types of priors. Some of these are frequentist methods, so you can see lasso is here right in this line, SCAD, a number of methods. What they did is they compared all of these different approaches over these different data sets, and then they looked at a number of summaries, so how well it did at point estimation, interval estimation, prediction, and then prediction intervals. And so everything was relative to kind of a prior that is in the BAS. This is a Zellner-Schau prior. It's based on a Cauchy prior. It has a lot of theoretical properties. It's not the fastest one to implement because it has a numerical integration step in there. But compared to everything relative to that, and then everything in terms of timing of algorithms, all the timing scores were relative to the lasso. Okay. And so you can see that on both these scores in terms of the predictive inference estimation, some of the methods that are in BAS actually are doing better than a number of these frequentist methods. But the other surprising thing is in terms of CPU time. And so that a number of these are actually better or faster than using lasso. Okay, so for the class of problems that it can scale up to, that was a surprise to me. I didn't pay them anything for doing that study, but again, I encourage you to read it, read the methods for that. Okay. All right, so in terms of advanced topics, as I mentioned, BAS does support generalized linear models. So currently there's implementations for doing logistic regression, Poisson regression, negative binomial. All of that model fitting is actually done with C and Fortran, kind of borrowing from a lot of the stuff that was there for CRAN going back in years, but implementing it all now at the C and Fortran level. There are a number of, again, research still going on in terms of prior choice for coefficients, particularly in generalized linear models. The book isn't quite written on kind of what are the best priors. There are a lot that are really good, but no one's done a really serious comparison looking at all of that. There are constraints on the model space, so this is currently implemented, but there are, again, still work going on that where we might want to have hierarchical constraints if you work with factors, if you have interactions, or hierarchical constraints, parental constraints. You can actually reduce the number of models that you're looking at significantly by forcing, say, main effects to be in, or if you have an interaction, all of the parents or main effects have to be included, et cetera. And that turned out to be an interesting counting problem that involved Bell numbers that ChatGPT couldn't solve for me. So anyway, can't do everything. Memory management for scaling to larger problems is an ongoing issue, and so that's where I'm actually be happy to work with other people that have solved some of that. So how do we scale up? I always buy a computer that has a lot of memory, or we have other workstations that have a lot of memory, but not everyone can afford to do that. So trying to be more efficient with some of the memory management. And then ongoing research of my own is looking at more advanced MCMC strategies and estimation approaches that can improve the results here. All right, so that's all I have to say. Thank you. If you're interested in looking at the code or contributing, the development version of it's on GitHub, and there's documentation there, and then on CRAN. So thanks.